Yeah.
Today is my pleasure to introduce the speaker, Professor Vadym Radchenko from Kyiv State University. The talk devoted to equation with a symmetric integral with respect to stochastic measures. Please, Vadym.
Thank you. Thank you very much for possibility to have a talk of this seminar. I would like to note that this work was partially supported by Alexander von Humboldt Foundation and carried out in our Kyiv University and in Jena University in Germany. The outlines of our talk are the following. We will give some preliminaries about stochastic measures. I had several talks on your seminar some time ago, but I think I need to recall the basic facts about stochastic measures. We will give definition of symmetric integral of a random function with respect to stochastic measure. Consider the ordinary stochastic equation with this integral. Consider averaging principle. And stochastic transport equations we will consider too. I think I don't know if we will have time for last two items. Maybe not, but we have also some materials about equations driven by stochastic measures. So please give your question at any time. And I recall the basic definitions. We have set of real valued random variables, L sub 0, arbitrarily set with sigma-algebra. And we call that stochastic measure is a sigma-additive mapping from arbitrary sigma-algebra to set of stochastic measure. Sometimes, sometimes this object is called measure with values in L sub 0. And we don't ask about some positivity, about moment conditions, about martingale conditions. We have no any special conditions for our mean. We say that this mapping is with values L0, L sub 0, and in this space we use convergence in probability.
Excuse me, Vadym. Can we understand this measure as a vector measure with values in the topological space L0, because it of course have topology related to convergence and probability?
Yes, yes. As I understand correctly your questions, the last sentence is equivalent to the definition.
Okay.
Yes. And I recall that we have no independence conditions and so on. So continue. And we have some examples. Of course, some stochastic process give examples of stochastic measures. Orthogonal stochastic measures, alpha stable stochastic measures defined on sigma-algebra. Of course, stochastic measures may be generated by martingales, by fractional Brownian motion. I recall some examples. Maybe I show all examples that I want to show. For stochastic process xt, usually we can generate stochastic measures on Borel subsets of segment by the following Wiener-type integral. And if for process such Wiener-type integral is well defined and have some limit theorems that ensure sigma-additivity in probability or sigma-additivity in other similar sense. If we have properties of Wiener-type integral of such kind, usually we have stochastic measures generated by our process. Not for all process we have such properties, but we have some essential examples you can see. Martingales, fractional Brownian motion, subfractional Brownian motion, Rosenblatt processes, and maybe some others. We will have some statement for stochastic measures, and it seems to me it is interesting that our statements for stochastic measure may be applied for wide class of stochastic processes. I gave a definition for arbitrary sigma algebra, and some statements may be taken for arbitrary sigma algebra, but in fact the main results of our talk will be taken if when we have mu on Borel subsets of a line segment, and such process has a continuous passes. Of course, this is some restriction on our stochastic measures, but for example, in our examples from 1 to 4, we have that such assumptions holds. More essential may be that this process should have continuous passes. For general stochastic measures, not necessarily with continuous passes, was defined an integral of deterministic measurable functions. Deterministic measurable functions. This integrals, in fact, was defined and studied approximately. I want to find possibility. Okay. Actually, so in years 90 and later, or approximately 90, such integrals was defined with basic as a results of Michel-Talagrand and some similar results about boundedness of set of stochastic of values of stochastic measure. If we consider such set where set A belongs to sigma algebra, set of all these random variables is bounded in probability. It is really difficult result defined by Talagrand, and with such basis it was possible to define such integral. Such integral was studied before, and I will not give much about this integral now. Our goal is consider random functions. Or such as we try to define integral of random functions with respect to general stochastic measure.
I'm sorry.
Okay, Georgi.
Well, the result of Talagrand says that for any stochastic measure, this set of values is bounded.
Any stochastic measure, yes, defined on sigma algebra. Of course.
Borel subsets. Yes.
Yeah, this result, no, any. I remember any sigma algebra. It was result approximately 91, as I remember exactly.
Okay, thank you.
And there are no any conditions that the sigma field is countably generated.
No conditions. No.
Okay.
Yeah. Similar result was obtained approximately in this year, maybe plus minus 1 year, by Kelton and collaborators, Nigel Kelton. But they consider some sigma algebra of 0, 1. They consider one example of sigma algebra. If I remember, Borel sigma algebra. But Talagrand proved in general set. And as some additional result, we have the following result. I will not give a proof now, that for any sigma algebra of any, for any stochastic measure on any sigma algebra, for any disjoint sets, for any collection of disjoint sets, all such sums, random variables of such type, are bounded in probability. This result also take place. And this is our basis to define a symmetric stochastic integral. And now I cannot say that I give a definition of stochastic integral, symmetric integral. This is a very standard definition. In fact, maybe in first used by Stratonovich, maybe somebody before Stratonovich used this definition. Definitions is absolutely standard. When we have processes Ct and integrator eta t, some random processes, we have any sequence of partitions with maximum tends to 0. We consider integral sums of symmetric type. And if such sums have a limit in probability, we say that the integral, symmetric integral, is defined. Absolutely standard definition. The question is for which processes eta and t this integral is well defined. I will not recall the Stratonovich integral definition, this is well known, but I can recall approach of Rami and Rousseau. This is an important method for me in our direction. They consider processes of finite cubic variation This means that some sums of, as I remember exactly, xi, t plus epsilon minus xt cubic divided by epsilon integral by t have some limit, uniform limited probability as epsilon tends to 0 as plus. For processes with such limit, they constructed integral of such type. Maybe I need take eta in this place. Integrator should have a finite cubic variation. And here should be a process which is a function of our integrator and time variable. They have some result. They, of course, have an example of process of finite cubic variation, but it seems it is not easy to check. The process has some variation. And we have this approach, and we took this approach and used for stochastic measure. We have the following result. Assumption A1, this means that our stochastic measure is defined on Borel subsets of line segment and has a continuous passes. Continuous process of bounded variations. In most of our situations, we will have this process is equal to t, and function if f is of such class. Then integral of such functions with respect to stochastic measure is well defined, and usual change of variable formula take place. I think need some comments to this formula, or it is easy to see that we have standard variation, standard situation. Here we have, in fact, f large first.
Yes, because it was unclear what is it.
Yes, It seems it's a standard formula. And for us, for me, it seems that interesting result that all such functions for smooth f are integrable. Such integral exists. And I can give outlines of the proof, not long, not complicated.
And what are assumptions on mu-t?
Stochastic measure on Borel subsets of this segment with continuous passes.
And that's all.
I recall that process 0 is continuous.
So,
yeah.
So you cannot take any continuous process mu-t, but somehow this property of sigma-additivity.
In fact, we need to have such integral of non-random functions. Wiener type integral exists and have some limit properties.
Yes, this property, Andrei, controls uniformly increments of mu-t. So I think that we can rewrite partial sums for the left-hand side and right-hand side, and
probably. And one more question. So there may be evidence between V of t and mu of t. So V is a stochastic process.
No. Sorry.
Continuous function.
Stop. Maybe not good word.
Continuous function of bounded variation.
Sorry.
Thanks.
Thank you very much. Thank you very much. And about the proof, we use standard Taylor formula by two ways. We estimate such difference where we have derivative in point xv, and we have another difference, the same but with sign minus, is a similar derivative in other points, and continues as here, and take the difference of two such qualities. Do you hear me? I trouble about my okay. Thank you. Thank you. And oops, a moment. Okay, I think everything is okay. And when we have difference, the main situation, the main idea that such elements are small value multiplied by x minus x1 square. So when we take such difference, divide our interval 0t by our points tkn, we have, and instead of x we can have mu. Here we have some squares of some sets, of some measures. This x1 minus x, this a measure, stochastic measure of small interval. And we have, here we have small o, na sum of such squares of our measures, our stochastic measures. Due to our lemma, we have such values are bounded in probability, and by this element we have that this value tends to 0 in probability. First elements after difference difference with coefficient 1/2. Other elements leads over to such values. And some elements leads to integral with respect to function of bounded variation, and some small values that tends to 0 when our partitions have a small mesh. So we have that this value tends to 0 in probability for respective partitions. Is it clear? May I follow?
Could you please explain one more time about the term 1/2 double derivative? Why this term disappears in a limit?
When we have a space here, which element? One more, Andrei.
This one.
Sorry. This one.
No,
Maybe
yes.
The same in another frame too. Yeah.
This means that we have 1/2 f11 prime in xp minus f x1 v1 after the difference and x minus x squared. We have a half of the difference. When we use this difference in this equality in each of these differences, we get 1/2. In close points, I don't want to write everything. These points are close. T, sorry. Yes, mu and t are close, and also mu is continuous. When these elements are close, values of mu are close. Sorry, here is minus. Mu are close and t are close. Second derivative is continuous. Second derivative of f large. This way, we have sub 1. In original publication, we use this Taylor formula with integral last term in integral form. And it's possible to see that this small o is uniform for all values.
And why do you need this second derivative with respect to the first variable?
Without this, because I need this square difference.
Okay, I see.
For stochastic process, I have
I understand. Thanks.
I have this small value, bounded value.
Also, I have a question. Where do you use that V is deterministic?
Sorry. Now I see. Maybe not important.
I think that it is not important.
Yeah. The word process also was possible.
Yes.
The crucial moment, bounded variation. Yes.
Exactly.
I guess that not process. Usual process have not bounded variation in my yeah. Sorry. Yeah. Thank you very much again. And thank you. May I go to the next slide?
Yes.
Yes. Of course, we can come back, but in Arami and Rousseau paper, some calculations more complicated because they use the third variable and cubic variation, and they complicate more complicated. So, moment. Okay. We have the whole also really some different and the whole you
Expect
the integral is very similar to, of course, properties of integral are similar to Stratonovich integral, only with that moment that we have integral only functions of such type. Only functions of such type. And this gives some restrictions to equations that we can consider. But due to Ramy and Rousseau, I can give a solution of such equation. We will give exact assumptions later. But of course, this is a symbolic writing that means the following. Of course, in standard writing, these equations means that xt equals x0 integral of such type, symmetric integral with respect to stochastic measure, and last term, you understand which one. In our case, this equation, we understand in the following sense. Of course, to define such integral, we need that x is a process of such kind, and process of bounded variation, of course, not only function in first, and for any process Zs of similar kind, we need to have the following equation. Of course, for such situation, we obtained a standard view of equation. But this is important to ensure a uniqueness. To get a uniqueness of the solution, we need some more restrictive equation, but the whole. And also, I will give main idea of solution of such equation. Only I want to know, I tried to consider equation with time variable in first term, but there are some problems, and maybe I will have later similar results, but not now.
Vadym, let me ask you the following. As far as I understood, you need additional point 2 in the definition of solution due to the problem when you study uniqueness. Usually, when we study uniqueness of the stochastic differential equation under Ito framework, we can use the estimation of the stochastic integral. So, am I right that you don't have a good estimation of your integrals using the integrand?
Yes, you are correct. We have absolutely another type of equations only because our integral is some functions of other variables, and if only I can say that this integral is bounded, is continuous, but other estimates are difficult. And
by the way, how do you can you prove that your integral is continuous as a function of the upper limit?
Because this integral is equals to such value with some additional terms.
Oh, I see. You use your formula. Okay, good. Okay, thank you.
And all time we take continuous continuous version of mu. All time we take continuous version. And we will follow. Okay, we use those. We will use those Zussman transformations, but at first I give some technical assumptions. In fact, technical, in fact, not very technical. We have some assumptions. Second derivative for sigma, continuity, and some boundedness, and Lipschitz assumptions on B. Not very important. Important assumptions on sigma, because for sigma we use those Zussman transformations. We consider large F that is a solution of these equations. And for such F, we take inverse functions with respect to second variable, and we have the following theorem. I only can take that my methods follow the methods of Aramis and Rousseau. Only in our settings we check that all ideas works, and for general stochastic measure it works. And A1, that mu is continuous on Borel subsets. A2, assumptions on our sigma and B. And under these assumptions, we have unique solutions, F mu yt, where it is solution of a random equation. The last equations may be solved for any fixed omega. We have non-stochastic integral. In fact, good functions, Lipschitz, and so on. So YC is well defined. And for proof of this theorem, we use only some substitutions. We take this process as elements of our equations, give some calculations, and equation holds. And using, as I remember, this value or similar value as process zeta from here, from here, or some special kinds of z, we obtain that solutions should be of the following kind. In fact, I can say that is in some sense non-stochastical results after definition of our integral. And
Vadym,
yes,
Vadym, can you just show okay, this theorem 3? Let me ask you the following. As far as I understood, this yt contains, like in usual Ito theory, some multiple integrals and nonlinear functionals from the past of our mu t. Because if you will solve iteratively this equation for yt, you will get the values of mu s from 0 to t. So this is like tail, like past of mu t, and you have such a representation. So the choice of f is unique, f capital.
Sorry, the question was very long. In short form once again, and my English may be perfect.
My idea is following. We expect when we have the initial equation that the process xt must depend on the past of the process mu t. And all this dependence now is smooth, as we see. Yes, it is contained in yt. And yt is a good solution to usual deterministic differential equation with good coefficients. So my question is the choice of f capital unique? Is such transformation to ordinary differential equation unique?
In this equation, of course, f is unique.
Yes, yes, in this equation unique, but this leads only to such. Can you prove the uniqueness if I say that, for example, I have another solution which has a form xt is equal some j capital mu t z t capital.
No. This is a good question, and I have this question when I try to. For last time I tried to consider equation with sigma depends of time variable. By approximations, I can construct the solution. Solution exists, but I have much problems with uniqueness. I tried to find some estimates. I did not have a success by today.
I see.
So
okay, thank you. Yeah.
Thank you for the comments. But you really see the essential problem here. I think we consider that equation, and for such equation also we have possibility to prove an averaging principle. For specialists in usual differential equations, this is a well-known situation. Maybe in stochastic equations is well-known too. But I recall in this situation that we have t divided by epsilon. For such positive epsilon, we find a solution of this equation and try to show that these solutions tends to solutions of some averaged equation by the following. We will have some averaged function bar b. For such equation, we also can find a solution, and we will show that we have the convergence of such type. This is standard situation averaging principle. We need to define B, and also this is some restricted results. We only have averaging in time variable from the second term. Good results, of course, have equation with t in the first term, t in the second term, and t divided by epsilon in each term. I would like to have something like this, but I have what we have. And we have some standard assumption. So for sigma and b, and for mu, we have our previous assumptions from our equation. Twice differentiable b with bounded derivatives, some assumptions of b, so that our equation has a unique solution. By the same way, this equation we have a unique solution from assumptions of b and definitions of bar b later. We will see that all assumptions will have. Only what I would like. Okay. And which assumptions on b prime bar b we have? I have the following. This is a nearly standard assumptions for averaging principle that for our functions b should exist a function bar b such that such integrals over all upper limits is bounded. Standard example, as I write correctly, sine ys, we integrate by s. Y should be bounded from for example, from 1 to 2, bounded from the 0 and from above. Periodic functions with some bounded period, is an example of such B. Assumptions A4 we will have for the part of our theorem. It is what is not necessary for general result, but is necessary for part of our result. And this assumption is also known for stochastic measures. You can see that for our stochastic measures exist some finite real valued measure. Finite, yes, I recall it finite, such that if square of function is integral with respect to m, then this function is integrable with respect to our stochastic measure. Some technical results in some places we will have. And under this
let me ask you, this is interesting that this is a sufficient condition. So it can happen that some other measured function also are integrable.
Yeah, sorry.
Can it happen that such measure m exists, but still there are some functions h which are not square integrable with respect to m, but still integrable with respect to our random measure?
Exactly,
so
yes.
This is just sufficient condition which give us a
subset of integral functions.
Suitable set of functions where we can work. Yeah.
Yes, exactly. Thank you. And our results is the following. Under our usual condition, sorry, maybe I omit our standard assumptions A1, but I told that we have that mu is continuous on Borel subset. This assumptions holds. These assumptions about B and sigma, that equations has a unique solution, and these assumptions about bar B. And under these assumptions, we have such limit for each omega, because processes are continuous, it's possible to obtain this. And under assumptions A4 about h squared dm, we have speed, we have such rate of our limit, epsilon 1 over 3. I don't give an probability on the proof on this slide. Maybe, as I remember, we will consider another, because this is only technical. In fact, we in this theorem we can concrete form of our solutions. Xt is f of mu y. Y is a solution of some equations. All functions are bounded and continuous. We have some standard in this situation technique to estimate some difference. Sorry, not very stochastic technique. Only difference between some values and some special divided of limit of segment 0 sub t, and use concrete form of our solution.
Okay, everything sounds good, but where you get this 1 over 3, because usually in non-stochastic case we have epsilon, and in stochastic Ito case we have epsilon 1 over 2 usually. But how did you find this 1 over 3? Why do you have it?
because we have it was more strange if we have one, for example, over half in a concrete situation, 1/3 in general. In fact, usual answer in such situation because of technical reason. I can say that in fact I can give some comment. I want to maybe one slide back. Okay. This assumptions looks strange in this this situation, but where I using without these assumptions, I can take that if fnx are bounded, values of these functions gives a convergent series. Then fn square, this series conversion is finite almost surely. For example, this holds when we have indicators. For general, under these assumptions, I have the following: if values of squares are bounded, for example, 1, then we have such property. And at some moment, I use this for some integral sums in our situations, get that some integrals fn d mu in square is finite. Also, we have some dividing, maybe 1/n or something like this. Our 2 divided by n, our segment. Estimate on each segment some difference. Estimate our bar b, and we calculate for which n we have both estimates corresponds. And after my calculates, it was appeared that epsilon 1/3.
Okay.
Yes, not in details. I can give later. Okay, I clear all drawing. And this is about first equation, ordinary stochastic equation. Also, 2 years ago, I published a paper about partial differential equations, so-called transport equation. I tried to find an equation where our symmetric integral can work. Not all equations work with this integral well, but for transport equations, we can find a solution and find some result. Such equation describes some physical processes, some transportations of some elements in fluid, and so on. This equation was studied in some papers. I used some ideas from other papers and see how these ideas can work for our symmetric integral. One of the good for me papers was paper Catundi and Oliveira in Theory of Stochastic Processes and Applications that is published in your department. This equation was studied when it was driven by Levy process, fractional Brownian motions. This equation is well studied for different processes. I cannot say that our results are generalization of these results, because in their result they can take sometimes t here. We don't take unknown functions here. We have function of such kind. And these equations we understand in some weak sense. In all papers, maybe in all papers, solutions is understood in the following sense, that we here have some functions phi of compact support and infinitely differentiable. And for such functions phi, the following equation should have holes. U should be measurable functions, and in this situation, of course, we need that this integral is well defined. For us, it means that this function, this integral should be some function of our stochastic measure and process of bounded variation. And standard techniques show that such U may be obtained. I did find standard assumptions. Last of them is technical. You see this assumptions. U sub 0 measure and continuous derivative. You will see that this will be important. Bounded. Some assumptions on B, but this derivative used in definition of solution. And assumption A2 really is used in proof also for some technical moments. But this is similar to assumptions in other papers for other processes. For our proof, we need Fubini-type theorem. Fubini-type theorem that integral, our symmetric integral with respect to dx may be changed. And I use only dx. It was enough for our equation, and also this is important when we estimate these integrals. We prove this theorem use that our integral is some function of our mu and t and so on, and some standard calculations give this fact. Maybe I can show you even shortly ideas of proof. I see that I have 5 minutes. And which way to solve this equation we have? We have an axial, some additional equation. Function b is from our equation, and plus mu t here. This equation has a unique solutions by standard considerations. Also, this process has a derivative with respect to t, and I show, sorry, with respect to x, not with respect to t because of such summon. And I show that our process has an inverse function. This derivative is positive, therefore inverse function exists. And theorem states that such process satisfies our equation. And under last conditions, our strange conditions or technical conditions on B integral is finite. Another conditions, under some additional conditions, bounded solution, bounded in such sense, is unique. If we have another solution, we have solutions of such kind, and solution of such kind which is bounded is unique. And about proof, I only show proof of existence. We take this in the equations, have some transformations. Have some transformations. Use our Fubini-type theorem, and not very difficult was to prove that equations holds. We start from our functions here and finish here. our process under after change variable. Sorry. After change of variable. Sorry. To sub-zero. We need to change variable here. X over s is a new variable, and we have here process from here. So sorry, not in details. Some calculations show that we have a solution, and proof of uniqueness is much more technical, and also in some sense maybe not very stochastical, but this is technique of work with our symmetric integral. When we get our usual chain rule for our integral, the following is similar to standard analysis, not stochastic analysis. Maybe I stop on this moment. If you have questions, you are welcome.
Okay, thank you very much for interesting talk.
Sorry. Maybe I can show some literature. Thank you. At the last, I have some references to other papers, and also I can say that there are some publications on this topic, not see to the last one, but also I have a book of year 2022. If somebody is interested in this book, you can ask me, we can talk about this. And now your questions, please.
Okay, thank you for interesting talk. It is always good to hear your talk about the progress in this interesting theory. Maybe somebody have questions or comments, please. Okay, let's start because I have several questions and comments. First of all, let me say that when we consider a Gaussian process, then I have a definition of so-called integrators, which are very close to your definition, because for integrators, we can integrate any L2 deterministic function with respect to it. But using Talagrand condition, that the sum which you mentioned are bounded in probability, we have that we will have convergence in L2 sense for Gaussian case. And it means that in Gaussian case, you get exactly the integrators like the example of such a measure. And I must say that we did a lot with it. So you can see my papers, or I can show you if you want. This is a first comment. Second comment is that maybe it's good to mention that there are a lot of different construction of the symmetric integral, as you said, and again, even for Wiener cases, Ogawa integral and
Ogawa is serious, maybe yes.
And Pardue-Protter integral. So there are a lot of different construction, and I think that they give the same answer if we will use your condition. But the question is how your integral is related to rough path theory, because you said that you need some 3 variation or something. So how it is related to rough path theory? You mentioned it, for example, frictional Brownian motion, and you constructed your integral. How it is related? What do you think?
Difficult question. I hear and I tried to study or to understand rough path theory in connection with our integral. I tried to see this paper, this theory. I did not find connection with my theory. Maybe I am not deeply involved in this theory. I tried, but I did not find the connection. I did not find the possible good connections. Sorry.
No, but you see, for example, it can be very useful when you consider this first ordinary stochastic differential equation, which you showed as a theorem one. Because in this case, they have, I think, a good statement when you just look for integrand of such variation that you can define at least Young integral when the variation of the integral integrand and the process which give you measure in sum is greater than one. Then why I am asking? Because we have seen your representation for solution. Xt is some good function from mu t at the time t, and all past is very good. And this past can contain multiple integrals with respect to this measure mu t. Actually, in rough path series, these multiple integrals are well defined. So you studying this theory, you can enlarge the possible set of possible solution, maybe.
Okay, thank you. I will see to the theory once more. Thank you for your comments.
By the way, actually, we discussed this with Terry Lyons, exactly this idea. Actually, it came from Schussmann and initially from Krasnoselsky about the characterization of the mapping which give you the solution of stochastic differential equation as a functional of the noise. And what can be this mapping? So it can be interesting. Okay, another comment is about the different equation. By the way, why you did not mention that you have a lot of results, and even your former PhD students have a lot of results about partial different boundary value, partial differential equation with this random measures too. And you mentioned that you study this transport equation with this kind of integral, just looking for another kind of integral. But I must say that there is a well-known book of Klatskin. It is rather old, like 1984, about the stochastic integrals in the physical systems. He's physician.
Yeah.
Yes.
No.
So you know this book. He used Stratonovich integral, and he gave a lot of examples of physical systems, whereas he think this Stratonovich integral is more suitable than Ito integral. So why don't check these models where you can say that noise don't must be generated by the Wiener process. Sometimes it is not very usual.
Sorry, one short answer. Of course, a solution should have a form function. This is some restrictions for solutions, but I will see. Maybe Klatskin book is useful.
Also, there is a book of Rozanov, maybe 1995, about also boundary value problems, about partial differential equations with Gaussian random measures. And he discussed a lot of properties of the solution, so on. And I think that it is not necessary to have the orthogonal Gaussian measures to get the at least in good cases when you have good partial differential equation, at least in good cases you don't need the orthogonality of this measure. And the last one is the following. And now the Anderson model is very popular. People do a lot. For example, Tudor do this. You mentioned him, and a lot of other people considered different noises in Anderson model. And they studied colored noise, white noise, different integrals, by the way. For example, this Yao Zong Hu proposed to study Skorokhod integral, but it is not necessary. It is not necessary. I think that your theory can be very well applied in this case, and you can study Anderson model with such noise which generated by your stochastic measure. I think it can be done. Yeah.
Thank you very much. I will see these papers, these books.
Okay, thank you. And also let me say that I am interested in your book.
Oh, sorry, no problem.
Okay,
Andrei, you can write me an email and
okay, very
no
very
problem.
nice. Thank you very much.
Thank you.
Okay, thank you again for interesting talk. And for today we finished our work. Georgi, do you know who is the next speaker?
Of course, I know it will be Mykola Vovchansky.
Okay, so see you next week. Thanks everybody, and bye.
Thanks,
Thank you.
everybody.
Bye.
Bye.
Goodbye.
Thank you. Bye.